Bismillahirrahmanirrahim. Assalamu alaikum. I'm Aniza Shehzadi from Physics Department. Today's my presentation is buffer capacity. What is buffer? Buffer are compounds or mixture of compounds that by their presence in the solution resist changes in the pH upon the addition of small quantities of acid or alkalis. What is buffer capacity? The buffer capacity of a buffer solution is a measure of its magnitude of its resistance to the change in the pH on an addition of an acid or a base. Buffer capacity is also referred as buffer index, buffer value, buffer efficiency, or buffer coefficients. The buffer capacity represented by beta may also be defined as the ratio of increment of strong acid or base to the small change in pH brought about by this addition. Beta is equal to del A or del B over del pH, where del A or del B represent the small increments in grams equivalents liter of strong acid or base added to buffer to bring about a pH change of del pH. According to the above equation, a solution has a buffer capacity of 1 when 1 liter of it requires 1 gram equivalent of a strong acid or base to change the pH by 1 unit. So smaller the pH change in a solution upon the addition of an acid or a base, greater is the buffer capacity and vice versa. What is the necessity of a buffer system? Sometimes it is necessary that a solution of a definite pH be prepared and stored. The preservation of such a solution is even more difficult than its preparation. If solution comes in contact with air, it will absorb carbon dioxide and becomes acidic. On the other hand, if solution is stored in a glass bottle, alkaline impurities from the glass may alter its pH. Due to these reasons, pharmaceutical solutions are buffered, as the buffer solution are capable of maintaining pH at some fairly constant value when even small amounts of acid or base are added. What are the types of buffers? Generally, buffers are of two types: acidic buffers and basic buffers. What are acidic buffers? An acidic buffer is a combination of weak acid and its salt with a strong base. Weak acid and salt with strong base are conjugate base. For example, CH3COOH, CH3COONA, H2CO3, NaHCO3, H3PO4, NaH2PO4, etc. What are the basic buffers? A basic buffer is a combination of weak base and its salt with a strong acid, i.e., weak base and salt with strong acid is conjugate acid. For example, ammonia, methane chloride, ammonia NH4 whole 2 CO3, NH4OH, NH4Cl. What are phosphate buffers? It's also called double salt buffers. Besides the two general types of buffers, acidic and basic, a third appears to exist. This is buffer system composed of two salts: monobasic potassium phosphate, which is KH2PO4, dibasic potassium phosphate, which is K2HPO4. What are buffer action? The resistance of a buffer solution to a change in pH is known as buffer action. Mechanism of action of acidic buffers. Consider a buffer system of CH3COOH, which is a weak electrolyte, and CH3COONA, which is a strong electrolyte. There will be a large concentration of sodium ions, CH3COONA, negative ions, and undissociated CH3COOH molecules. When an acid is added, if a strong acid HCl is added in CH3COOH, CH3COONA buffer, the change that will occur may be represented as CH3COONA sodium carry positive sign plus CH3COO negative. If we add CH3COOH, then H positive plus chlorine negative, and it will make HCl, hydrochloric acid. The hydrogen ions yielded by the HCl are quickly removed as unionized acetic acid, and the hydrogen ion concentration is therefore only slightly affected because acetic acid produced is very weak as compared to HCl added. When a base is added, if a strong base NaOH is added in CH3COOH, CH3COONA buffer, the change that will occur may be represented as CH3COOH, which is CH3COO negative plus H positive. If we add HO, then OH negative plus sodium carry positive sign, and it will make a sodium hydroxide, which is a base. The hydroxyl ions yielded by the NaOH are therefore removed as water, the supply of hydrogen ions needed for this purpose being constantly provided by the dissociation of acetic acid. Mechanism of action of basic buffers. Consider a buffer system of NH4OH, which is a weak electrolyte, and NH4Cl, which is a strong electrolyte. There will be a large concentration of NH4 plus ions, chlorine negative ions, and undissociated NH4OH molecules when an acid is added. If a strong acid HCl is added in NH4OH, NH4Cl buffer, the change that will occur may be represented as NH4OH, NH carry positive sign, NH4 plus hydroxyl negative. If we add OH, then H positive plus chlorine negative, it will make the hydrochloric acid. The hydrogen ions yielded by the HCl are therefore removed as water. The supply of hydroxyl ions needed for this is constantly provided by the ammonium hydroxide. What are the buffer equations? Henderson-Hasselbalch equation for acid buffers. The pH of acid buffers can be calculated from the dissociation constant K of the weak acid and the concentration of the acid and salt used. The dissociation expression of the weak acid can be represented as H positive plus A negative. Ka is equal to H positive A negative over Ha, or H positive is equal to constant Ha over E negative. This is a equation for acidic buffer. For basic buffers, buffer equation for basic buffers can be calculated in same way that for acidic buffers. Consider a basic buffer composed of a mixture of weak base and its salt. The dissociation constant for base can be written as BOH B positive plus OH negative. Then Kb is equal to B positive hydroxyl negative over BOH. Hydroxyl negative is equal to Kb BOH over B positive. This is the equation for basic buffers. A weak base is only slightly dissociated, and its dissociation is further depressed by the addition of salt, which provides B positive ions, which is common ion effect. As a result, the equilibrium concentration of the unionized base is nearly equal to the initial concentration of the base. The equilibrium concentration of B positive is assumed to be equal to the initial concentration of the salt added, since it is completely dissociated there. Therefore, in above equation, we represent concentration of B positive by salt concentration. What are the significance of Henderson-Hasselbalch equation? By this equation, the pH of a buffer solution can be calculated from the initial concentrations of the weak acid and the salt provided when K is given. However, the Henderson equation for basic buffer will give pOH, and so pH can be calculated as pKw is equal to pH plus BOH. If we find the pH, then pH is equal to pKw minus pOH. If pKw is 14, then pH is equal to 14 minus pOH. Also, the dissociation constant of a weak acid or a weak base can be calculated by measuring the pH of a buffer solution containing equimolar concentrations of the acid or base and the salt. Applications of buffers. The applications in biological systems are: the pH of blood is maintained at about 7.4 by 2 buffer systems, that are primary buffers and secondary buffers. Primary buffers. These are present in plasma. The plasma contains carbonic acid, carbonate, and acid alkali sodium salt of phosphoric acid. Secondary buffers. These are present in erythrocytes, which are oxygen, hemoglobin, and acid alkali potassium salt of phosphoric acid. In pharmaceutical systems, buffers are widely used in the field of pharmacy as ingredients in most of the pharmaceutical formulations in order to adjust the pH of the product to that required for maximum stability. In parenteral preparations, i.e. injections, in case of parenteral preparation, pH should be considered carefully as large deviations of pH may lead to serious consequences. The ideal pH of a parenteral product is 7.4, which is the pH of blood. The most commonly used buffers in parenteral products injections are acetate, phosphate, citrate, and glutamate. In ophthalmic preparations, i.e. in eye preparations, buffers are generally used in ophthalmic preparations to maintain the pH within the psychological pH range of lacrimal fluid, i.e. eye fluid. The lacrimal fluid has a pH in range 7 to 8, but it has good buffering capacity and can tolerate preparation having pH values between 3.5 to 10.5, and can tolerate preparation having pH value between 3.5 to 10.5 with little discomfort. Outside this range, i.e. 3.5 to 10.5, increased lacrimation may occur with other complications. The buffering agents most commonly used in ophthalmic preparations include borate, carbonate, and phosphate. In ointments and creams, topical products which are used on skins, such as ointments and creams, are also buffered to ensure stability of the formulation. The most commonly used buffers in ointments and cream are citric acid, its salts, and phosphoric acid. Phosphoric acid and its salt. Thank you so much. This is my presentation about buffer capacity.